We've now derived these beautiful isolobal relationships between metal fragments and organic systems, right? And we're now going to use them to do something else. So just to remind you, these are the isolobal relationships we derived a moment ago. And we derived them from first principles, from molecular orbital diagrams, and convincingly showed that these items, let's call them items, are isolobal. And they fulfill the requirements, to use your phrase. It fulfills the requirements. Okay. Now this is again that table I showed you. This is a summary of isolobal relationships. I don't expect you to memorize these. I did expect the master students in Berlin to memorize them, but I won't do that with you, because I know it's going to cause a lot of unhappy students. Anyway, you can do it. You can do it if you want, from first principles. Draw the molecular orbital diagram and you'll see, that it's isolobal. But anyway, I've already told you which are the important ones to know. Incidentally, it's interesting to see that you also have isolobal relationships with boron-containing compounds. And that's now where we're going to now move. We're now I'm going to take a step away from isolobal theory for a moment, and then I'm going to come back to it. So keep isolobal theory in your mind. Right. And what we're going to do is we're going to use isolobal theory to build things up according to something called polyhedral skeletal electron pair theory, using something called the Wade-Mingos rules. Now I know that's a mouthful, but essentially what we're going to do is we're going to, at the end of this lecture, take a molecule, any molecule, break it down into building blocks, fragments, analyze those fragments, and then put the molecule back together again. Right? And then we're going to predict the structure of the molecule. And that's basically what polyhedral skeletal electron pair theory is all about. It's considering a molecule as a cluster of building blocks with electrons that go into that cluster and go where they need to go. Now, the most common of these are the borane clusters. Now, typically how this is taught, and I really don't like the way that it's taught, typically in a second year class, is that you have the boranes and students sort of memorize this according to the so-called Wade rules. Now, I'm going to do it a bit differently. I'm going to go straight to the Wade-Mingos rules, which are much more logical and conceptual than bothering about the actual Wade rules, which apply only to boron-containing clusters. It's very limited. Okay, you can also use it for carboranes, but okay, I'm not going to go there. I just want to show you, that boron is a very special element because it has the propensity to form clusters. Now today's all about clusters. Here we have what are so-called closo boranes. And you'll see where this closo comes from in a moment. We have a range of closo boranes here. As you can see, these are some examples, right up to B12H12, B5H5. So you see, we're just increasing the nuclearity. Those are the closo boranes. Now, how this works, essentially, is if you go from a closo structure, now closo obviously means closed, and you pluck off one of the vertices, right? So let's imagine I start off with this closo borane, which is B6H6. It's one of these. There it is. It's got an octahedral arrangement of boron atoms. And, well, it's 2- charged. And let's now imagine I pluck off one of these vertices. What am I going to be left with? Well, I'm going to be left with one less boron atom. Don't worry about the H's too much. I'm going to be left with one less boron. And when I do that, when I pluck off a vertex from a closo structure, it goes, we call it nido. Closo-nido. If I take the nido structure and I pluck off another vertex, right, I go to arachno. Right? Now why arachno? Yes, it looks like a spider's web. So we have closo, nido, arachno. And if I were to take the arachno structure and pluck off another vertex, say that one there, so just take that away, I would have something called hypo, and so on. So that's sort of how this works in a very simplistic way. We're going to go into the details now, but you always start with the closo structure, taking of vertices, closo, nido, arachno, hypo. And by the way, you also have, it goes in all directions. Okay. So these are the wave rules for boranes, right? And this is what students learn, they memorize this, and then when the semester is over, they forgot all about it. Isn't it, Mitch? So, basically, if you know the formula of a borane, because boranes are clusters containing boron and hydrogen exclusively, if you know the formula and the charge, you can predict the structure type according to something called the Wade rules. These are essentially the Wade rules here. So let's have a look. Here we've got B5H9. That would be nido type because it fulfills this formula here. BNHN plus 4, B5H9 nido. Now, nido says something about the way the thing looks. I'll show you in a moment. Let's look at another example, just to show you how the wave rules work. B6H62 minus is closer because it falls into this, it fulfills this requirement here. Arachno, B4H10, B4H10 fits, and so on. You also have hypo, right? Hypo, remember, is if I take arachno and I pluck off another vertex. Those are essentially the wave rules for boranes. Okay. Now, just again to show you what we're actually doing here, we start with the closo structure, we remove a vertex, we get nido, we remove a second vertex, we get arachno. By the way, you can go in the other direction. You can add a vertex to the closo. You can add a vertex, and that's called hypercloso. You can remove a vertex from arachno, and what do you have? Hypo, right? And you can remove another vertex from hypo, and you have something called clado. So let's write those terms down. Closo, nido, arachno, hypo, clado, hypercloso. You see, that's based, and you can actually have other variants as well. In principle, you have like hypercloso and stuff like that. I mean, I think this is pretty good enough. So if we go from here to here, we're removing a vertex each time. This is how this works. Minus a vertex, and so on. And if we go in the other direction, obviously, we add vertices. So it goes in both directions. Now what this is, it's a game of Euclidean geometry more than anything else. It's taking shapes and playing with them. It's taking shapes and playing with them, looking at the number of heavy atoms, and thinking about the number of so-called skeletal electrons. Because the relationship between the number of vertices and the number of skeletal electrons is going to predict whether you have closo, nido, arachno, hypo. So it depends on those two parameters and their relationship to each other. And that's what this is all about. That's the Wade rules for boranes. We're going to extend this now using isolobal theory. But this is just to show you the whole picture. This picture, in fact, is in Alschenbroich. And you can see that this is essentially how it works. So what I've got here are all the closo structures. Now, closo is really, you can think of the closo as like the parent geometry. Right? It is a Euclidean, or let's say it is a polyhedron. It is a polyhedron that's closed. So the closo, if you've got 4 points, the closo polyhedron will be tetrahedron. If you have 5, trigonal bipyramidal, octahedral. and so on. You see? And that's how we go down. And notice what's happening. If I take, for example, this B12 structure here, and I remove the red vertex, that's what I'm left with. So what would that be? If that's closer, what is that?
Nido.
And what's that?
Ragno.
Yes. You see that these kind of resemble, these arachnostructures here do somewhat resemble a spider's web, don't they? Hence the name arachno. Now, this is a very interesting thing. If we have, for example, if we look at this series here, here we have a B6, so this would be closo-octahedral. If we pluck off this red vertex, what are we left with? Nido. And if we take that away, we're left with arachno. So you can see how this works, right? And in principle, I could take away another vertex and I'd get to hypo, and another and I'd get to close. So this is not complete. This is just showing you like a snapshot of all the possible geometries for boranes. Yes?
Can we have like lower configurations, like it stops before closo?
Yes, very good question. Yes, you can. You can have C3 closo. Not C3, but you can have a trinuclear system that's closo. Yes, which will just be essentially three atoms bound in a triangle. Yes.
For the nido, I know that means nest, and you can also see that it actually looks like that.
Yes, exactly. Nido is nest-like. That's right. So now you can see these sort of look like nests, right? Like birds' nests. Especially this one. Look at that. That's a real nest. So yeah, they all mean something. All right. So that's basically how it works. Now we're going to take this knowledge of the wave rules, and we're going to combine it. We're going to combine it with isolobal theory. We're going to arrive at something fabulous. All right. So in fact, what we're going to do now is we're going to find a way of analyzing structurally molecules, clusters, any molecule under the sun, by breaking it down into building blocks that we can analyze using isolobal theory to figure out the number of so-called skeletal electrons and then predict the structure time. That's what we're going to do. All right. So let's do that. All right. Now before we do that, I just want to show you. Right. So that's what I just basically said. We're going to take a generalization of the wave rules to anything. It's a logical and a conceptual approach called the Wade-Mengos, also the Wade-Mengos-Rudolph rules, which employs isolobal theory that we can deconstruct any molecular species under the sun into building blocks. The building blocks are then analyzed, and then we figure out how many skeletal electrons come from those building blocks into a cluster that we're going to build up from these fragments, and then we count those electrons, look at the nuclearity, and using what we have here, we can predict the structure time. How cool is that? So by looking at the relationship between the skeletal electrons, or the skeletal electron pairs, it doesn't really matter which you use. I use skeletal electrons. This is everything here just divided by 2, right? If you look at the relationship between n, which is the nuclearity of the thing, and the number of skeletal electrons, it gives you the structure time. Don't worry, we're going to do examples. Because the only way to understand this is by doing examples. Let's do it. Let's just jump right in. All right. Let's take... So we're going to do a Wade-Mengos analysis of a cluster. Let us take RH4CO12. Now I'm going to write down the steps. How do we do a Wade-Mengos analysis? The Wade-Mengos approach. The first step is to take the molecule or complex or whatever you have and deconstruct it into building blocks. Deconstruct into building blocks. 2, the second step is going to be analyze the building blocks using isolobal theory. And isolobal theory is going to tell us how many electrons each building block is going to be able to contribute to the cluster that we're going to build from those fragments. Get the number of skeletal electrons from the fragments from step 2. We'll do it, I'll show you how it works. And then basically using what we have here, this relationship between the nuclearity and the number of electron pairs, figure out structure type. All right. So let's do that. Those are the steps for the Wade-Mingos approach. And again, you can do this for any molecule under the sun. It's not restricted to boranes, it's not restricted to clusters, it just works for everything. Let's now take this example, RH4CO12. We're going to deconstruct it into recognizable building blocks where we can use isolobal theory, step 2, to analyze those building blocks. Then we're going to put the building blocks back together again to make the cluster, and we're going to figure out the structure type. Now, how would you break that thing down into recognizable building blocks?
Rhodium tricarbonyl.
Yes, rhodium tricarbonyl. Excellent. So that thing, RH4CO12, is in fact RHCO3, RHCO3, 4 of them. Does everyone agree? That's a reasonable building block. Now RHCO3 is what? We saw this in the last lecture. It is what? It is isolobal. Okay, before we get to isolability, what is it? Is it D6Ml2, D9Ml4? What is it for a fragment?
It's 9
Group 9?
Group was it?
9ML3.
D9Ml3. Yes. So our building block is rhodium tricarbonyl, which is D9ML3. D9ML3. Now a D9ML3 fragment, we said is isolobal to what? CH. Carbine. Right, now is the key point that everyone must pay very close attention. What do you see in that over there? What's that?
3 low electrons.
There's 3 electrons sitting there. So this is a D9ML3 is isolobal to this. So in fact, RHCO3 also has 3 electrons. So think about it. What we're doing is we're taking an RHCO3 fragment with these 3 electrons, we're taking 4 of them, and we're putting them together like Lego. And that means if we put 4 of those fragments together, how many electrons will be available to glue them together? 12. So from this analysis, we conclude that we have so each fragment, we have for each fragment RHCO3 3 skeletal electrons. In total, 12. Now that's the point. There were 12 electrons in total, 12 cluster electrons. What is the nuclearity of the thing? 4. So, what structure type does it have?
Oh no, Nido.
Yes. Nido. Good. Why?
Because n equals 4 and that makes 12.
Exactly. If n equals 4, the nuclearity, plus 4 times 2 is 8 plus 4 is 12, it's Nido. Very simple. Very simple. From using isolobal theory, you can predict the structure type just from breaking it down in a logical way, not memorizing Wade rules or anything like that, but using isolobal theory, which is all about understanding stuff. All right, so
Wait, what was it now?
Nido. Because remember, we have 12 electrons in total because okay, let's start from the beginning. There's the complex. Right, everyone pay close attention. We broke it down into 4 of these building blocks. Each of those building blocks is a D9ML3 fragment. Because it's a D9ML3 fragment, it has 3 electrons available to glue these things together, the so-called skeletal electrons. In total, therefore, 12. The nuclearity of the cluster is 4. So in other words, we need to find, in this table, something that fits. Now another way of doing it is just a much simpler way is to do it like this. To say 2n plus something equals 12. We know n is 4, because it's a tetranuclear cluster. So 4 plus what equals 12? Sorry, 8 plus what equals 12? 4. And if it's plus 4, it is Nido. That's how it works. Closo, Nido, Arachno, Hypo. Hypercloso, or capped closo, bicapped closo, clado. There it is, all of them. All of them, well, I mean, they go, you in principle go all the way. You have bicapped, tricapped, tetracapped, octacapped, yeah. Yes?
What's the skeletal electron pair section for?
Well, just this is basically exactly the same as this. It's just some people prefer to use skeletal electron pairs. I prefer to use skeletal electrons. It's exactly the same, just divided by 2. In fact, you can ignore the middle column if you want. I've put it there. Some people like to work in terms of skeletal electron pairs. I don't. Yes.
If you have if you have a cluster with a multitude of different ligands, if you have exotic stuff everywhere, you have to break it down into each blocks and analyze that separately?
Yes.
Or can you just take one and take the as everything?
Very good question. We have a very simple example here, which is homonuclear. It is it is an absolutely well, it's just a carbonyl ligands. It's totally homoleptic and homonuclear, so it's very simple. But of course, if you have mixed metal clusters, you have to break it down into different clusters or different building blocks, analyze those using isolobal theory, and then put it all back, simply put it back together again, if you will, in your mind, the glue being those electrons which we get from isolobal theory. How cool is that? You can do the same with these stupid boranes, by the way. Because boranes are isolobal with CHs. Right? There's an isolobal relationship between B and C. So now, next question. Here's a question. Here's a question. With which molecule is this guy isolobal? With which molecule is this cluster isolobal? Sorry? No. What would the formula be? Well, look. C4H4. We have 4 of these building blocks. Look at this isolobal relationship here. Look at that. This is composed of 4 of those. That is isolobal with CH. So that thing as a whole is isolobal with what? C4H4 exists. And it looks like this. It's called tetrahydrate.
Not like a Aromatic.
It's not aromatic at all.
Aromatic butane.
No. It's not a butadiene ring at all. It is sp3 hybridized carbon atoms bound together. This cluster is isolobal to tetrahydrate. And that, by the way, therefore also has what sort of a structure type? Sorry, no, what sort of a structure type? Nido. You see these relationships emerging. So that is, in fact, Nido. Let's do another example, right? I want you guys to be comfortable being able to do Wade-Mingos analysis on anything. All right. Right. Let's do one. In fact, let's take something silly. Benzene. All right, is there a problem?
No, it's okay.
Let's take benzene. C6H6. Now, I'm taking benzene specifically because I want you to appreciate that this Wade-Mingos approach works for everything, even a stupid little organic molecule. We can think of benzene, in fact, as a cluster that is composed of 6 carbynes,
Yeah.
and that it's in fact a cluster. It's a totally different way of thinking about it. Let's do the Wade-Mingos analysis for benzene. How do we proceed?
Break it down into 6 CHs.
Correct.
And each one has 3 electrons, so I have 18.
This is actually quite simple because it's already, we don't even need isolobal theory, really. So exactly, we have a total of 18 cluster electrons, or sorry, skeletal electrons. And then,
It's
Yeah.
Colorado.
36.
It's 2n plus 6 because n is 6. If it's 2n plus 6,
no, it's not 2n plus 6, n is 6, so it's 2 times 6.
Oh, oops.
Yeah, so 12.
So 12 plus what? So how many cluster electrons do we have in total? 18. So what do? This is what we do. Let's do it. 2 times 6, because the nuclearity is 6, plus something must equal 18. So what is that something? Solve for that something. Well, it's 6. Now, if the nuclearity is 6, if we have a plus 6, what do we have? You see, the important thing is, what the important thing is to find the plus what? You know, there it was plus 4, here it was plus 6. If it's plus 4, it's nido. If it's plus 6, it's arachno. If it's plus 8, it's hypo, and so on. Alright? Now what does that mean? It means that benzene has what sort of a structure? Yes. And that seems reasonable. Because if you think about benzene, it does look like a spider's web, kind of. So you can think of benzene in a completely different way to the traditional way, which is, you know, sp2 hybridized carbon, tralala, and all that. You can think of it as a cluster bearing 6 carbynes, each giving 3 electrons to the cluster, and that you end up with an arachno cluster type. So, that's basically how that works, the Wade-Mingos approach. And I want us to do some further examples, because this is, I think, very important. With which cluster? Give me an example of a cluster that is isolobal to benzene.
So the 6 with 18 cardinals?
Yes, exactly. So, that doesn't exist, by the way. But according to the predictions of isolobal theory, if it did, it would have probably the same reactivity as benzene, or at least comparable. So you see, there's 2 things here. It's breaking it down into fragments, analyzing those fragments, putting it back together again, and figuring out what structure type you have. But it's also realizing that once you've broken it down into these fragments, you can immediately sort of say it's isolobal to some known organic molecule, and that kind of helps. All right, I want us to do another example. Let's look at OS3 CO12. All right, how do we proceed? So we break it down into reasonable fragments. Josh, what do you think would be reasonable?
OSCO4.
Correct.
Thank you.
So we have how many of them? 3 of them.
Yeah, that makes sense.
All right, now what's that? Mitch. OSCO4, what is that? Osmium is in group 8.
T8MO4.
Iron, ruthenium, osmium. So what is that for a fragment?
Carbene. Carbene.
Sorry?
Carbene.
Okay, don't say that so quickly, that's right, but how did you arrive at that conclusion? Do it stepwise.
T8MO4,
Yes.
which is isolobal to CH2.
Right.
So it has 2 electrons, and there are 3 of them.
Yes.
So 6.
Alright, so we've got in total 6 skeletal electrons. Yes, go on.
Nuclearity is 3,
Nuclearity is 3.
so it's just 2n.
So,
Because-
so what is it going to be?
2n plus 0
Which
equals
is?
capped closer.
Yes. Capped closure. Now that doesn't make much sense, right? Because it's a trinuclear cluster. But the way to think about it is that for that family, the closure would be just 2 points, and if I add a third point to that you get capped closure. So it's kind of like that. Capped means that you take the closure structure and you add another vertex. It's also, some people call it hyperclosure, right? So this sort of seems a bit strange because, I mean, you basically got OS3CO12, we know it's a triangle. It's a bit odd to think of that as capped closure, but think of the closure structure as just 2 points on a line. That would be closure, and if I add a third point, it's capped closure. All right, now I want us to do a more challenging example. Just a moment. Alright, well, I know it's online. It's from the University of Bonn, which has some very nice examples. So we've done some simple examples. Now let's look at some more difficult examples. Some very nice notes. Unfortunately, they're in German, but that I was using when I was teaching this in Bonn. We have internet access. So that's basically how it works. And there we go. You see, this is my doctor father, Filippo, who is the son of who?
Fisher.
Yes, Fisher. All right. So, in fact, I don't mind using these because actually he took these, I realized, from the lecture of Hoffman. So, you know, okay. Anyways, now. Here you see some crazy molecules. I'm not going to go into these the tails. Alright, I just want to find a nice example. Are you ready? Alright, let's look at this one. Let's look at RH6CO16. Now, I said a moment ago, that benzene would be isolobal to what? Nicole, you said it. Rhodium 6C. Exactly. So it doesn't exist. But what does exist is RH6CO16, so a hexanuclear cluster. Now let's look at the Wade-Migos analysis. All right, it is in German, but we're in Europe, so it's an important language. So let's throw a bit of German into the mix. All right. So don't worry. Come on, guys, let's concentrate. What are we doing here? What is the problem with this molecule? Now, the ones we've looked at now were easy. We could divide them up.
We have an integer number of ligands.
Exactly. So what are we going to do? Well, we can add 2 carbonyls, because if you add ligands, so that we can break it down into fragments that we can analyze, it's not going to change the way, it's not going to considerably change the way that those metals are bonding to each other, i.e. it's not going to considerably change the structure type. So you can take ligands away and you can add ligands to help you with this decomposition process. So what we're doing here is we add 2 carbonyls. But if we add 2 carbonyls, we're adding effectively 4 electrons to the cluster, aren't we? So to compensate for that, we have to take 4 electrons away. So in fact, RH6CO16 is, let's say, the same as RH6CO18 4+. Do you all follow that? I'm adding 2 carbonyls so that I can do this decomposition into these fragments and then use them. And now we can proceed as we did before. We now have 6 of these. We now have the integer number of the CO18, 6 from RHCO3, and there we go. We know that RHCO3 is D9ML3. It is isolobal to CH. So in fact, what we establish, if you do the whole analysis, is that you end up with a closed-O structure.
What? So we just forget about the charges when we do this?
No, we don't. No, we don't. Where do the charges come in? Yes, 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 yes. Because we've, you see, that's the thing. We've made the whole thing 4+. So you've got to take that into consideration. You've got to take that into consideration when you do the electron counting, right? And then you go back to our table with 2n plus 2, 2n plus 4, 2n plus 6, and you figure out the structure type, and you will see that it is closed-O. So the charge on this thing is 4+. Now, check it out. There's some serious, does everyone follow? Everyone? Mitch? In the front here, Connor?
I don't really understand the arithmetic he's done. The
Yeah,
last
since
step,
that's
6, like 4 plus 1 minus 2.
All right, let's do it together. Abzählen. Alright. Lass uns das jetzt ganz in Ruhe machen. So, was machen wir?
Zahlen wir, wie viele Metallzentren, wie viele Metallzentren wir haben.
Okay, lass uns jetzt ernst sein. Aber ich habe das immer auf Deutsch unterrichtet, also das macht Spaß. Ne? Aber ihr versteht das nicht, oder? Ja, das sind ein paar Leute, die hier Deutsch verstehen. Du auch? Ja, ein bisschen. Lass uns das auf Deutsch machen.
Auf Deutsch?
Alright. Everyone
Yes, we use practice.
I'm just joking, I'll do it in English. Alright, we start off with RHCO16, and we are happy with that because we can't decompose it into fragments which are useful. So in order to fix that problem, we add 2 carbonyls. Now carbonyls, remember, have 2 electrons, so they're adding 2 electrons to the cluster. So in fact, we have RH6CO18, right? But now to correct for the fact that I've added 2 electrons, I've got to decrease the charge of the cluster by 4. So it becomes 4 plus. Okay, now, let's do the Wade-Mingos analysis. We have 6 RHCO3s, which is 6 times 3, because each unit gives 3 skeletal electrons, is 18, all right? And so now what are we going to do? We're going to say 2 times n plus something equals what?
18.
Right, 18 minus 4 is 14.
Yes.
Good.
Yes, we've got, because the thing is 4 plus charge. That's where the charge comes in. You see that? So 2, what is the nuclearity? 6. Plus what equals 14? So what is the structure type? Close. So this charge issue, you can fix. So I mean, he's done it in a different way, but I mean, this is basically what he's done in one line there. Is basically what we do here. So it's closed. Now, what is that thing going to look like? Yes.
He has 12 there, not 14. So, marks-wise, it should be 14, I think. Sure.
Well, he ends up with closer. I don't know what he's done there,
He
but
calculates the two and it's the same.
Yeah.
And then he uses 14 as 2. Like the 12 is the 2 and
yeah, there's the minus 4. You see, so yeah, look, he's taken. It doesn't matter. I mean, the way that I've done it is anyway the way I want you to do it. I want you to do it step for step. So these are not my notes. So now, what does that mean? What is this thing going to look like? What is a closo? Closo means closed. And what is a closo structure that has 6 vertices? It's an octahedron. What is a closo structure that has 5 vertices?
Trigonal bipyramidal?
Trigonal bipyramid. What is a closo structure that has 4 vertices? Tetrahedron.
Yeah.
What is a closo structure that has 7 vertices?
Seesaw, is it? No, no,
Yes. A pentagonal bipyramidal. Pentagonal bipyramidal. Basically, a pentagon with 2 vertices. And so on. The point is, closo structures are structures that you derive from the, let's say, it's basically a game in playing with shapes. You know, like the Greeks used to have all those shapes. That's what you basically do. But polyhedra. That's why it's called polyhedron skeletal electron pair theory. You see, it's very descriptive. All right, so now that's a closo structure type, but there's some other implications here. For example, using isolobal theory, we establish that RH6CO 184 plus is isolobal with what?
Benzene?
C6H6
Correct. So if you imagine a benzene ring, think about this crazy situation that has a 4 plus charge, it would have a closo structure. You have 6 carbon atoms. In other words, see, it would look like this.
That shit's crazy.
It would be closo, C6H6. And by the way, you can also figure out, it's also using isolobal relationships, you can relate it back to boranes. Incidentally, it is isolobal to B6H62 minus, which is one of the simplest closo boranes. Let's have a look at it. Oh, whoops. It's in my actual. We encountered it earlier. Here he is.
Really low is good.
So B6H62 minus is isolobal to this guy over here, which is isolobal to this guy over here. So, yes, there was a question.
With the benzene ring, like, wouldn't that be like 6 times CH?
Yes.
So that means wouldn't that be like the same as the 6RH CO3? So that means the same as the ion?
Well, rhodium is in group 9, remember? Remember, this thing is not charged,
Yeah.
right?
So wouldn't that be equal to the charge?
What? Or you mean, is this isolobal to C6H64 plus? Well, yes, it is. We just showed that. Because it is composed of 6 RHCO3 fragments, each of which is isolobal to a CH. But remember, the whole thing has got a 4 plus charge. That's the point. Now, I want us now to do one example together. I'm not going to give you the solution. I want you guys to do this. This is a very cool cluster. OS8 CO23. So an octanuclear cluster. OS8 CO23. That's a big ass cluster. Actually, no.
Oh, I didn't know.
No, do that. No, I think do that. I mean, it's a little bit difficult because we haven't done one of these isolobal relationships. So es ist egal. Versuch das mal. Try. So yeah. All right, try and do that, because that's a very challenging one. And just to assist you, I'm going to give you some key isolobal relationships that are. So this might come in handy. So what do you guys think? Das ist schwierig. Das ist gar nicht einfach.
Haben wir jetzt ja schon gelöst.
Hast du das gelöst? Ja, das ist nicht so einfach geglaubt.
Kan ik nog wel eens een, was dit nog een keer waar voor die verschillende
But why? It's such a nice language.
Yeah, but if it's something important and we don't understand.
No, we're just having a conversation. It's I'm not teaching. It's just a silly little joke. Please stop just speaking German, please.
Well, the SVE is practically little Germany in the university, so why not?
All right. How are we doing?
Trying.
What did you get your isolobal relationship to? Carbine?
And it's the same line as carbine.
The DAL3 is related to just naked carbon.
Oh, it's like
Oh, wait, osmium
Which makes it
210.
huge. It's like plus 16.
Two electrons.
Yeah,
It's crazy.
yeah. And so then
I love hearing how you guys struggling away through a problem.
So that's for like
This is like super caps. Like,
It is-
Okay,
it
so
is.
let's see.
You're gonna see.
For like
I don't know what to call it, but it's just like
Yeah, I get it.
amount of package.
Oh,
Are you are you assistant?
teachers assistant.
Don't be arrogant, Mitch.
It's going to be crazy. It's like plus 16.
Mitch.
It's insane.
You got a plus.
Just helping with the small
Yeah.
things.
Yeah.
oh yes, I wonder that.
Oh no, wait, no, it's plus 2. It's plus 2, so I've got to do that. So it's just like what? Plus, oh, it's only like plus 40.
Ta-da!
Da-da-da-da.
Thank you.
Alright, you gotta break it down into building blocks, guys. Alright, let's have a look at the solution. Oh shit, it's half past.
Yeah.
I'll show you.
Alright, I'm going to give you the solution. That is the solution. It is a bicapped bis closo, if you will. Zweifach überdachtes an octahedron, which essentially has two additional vertices. That's the structure. The way that it's done is you've got to break it down into OSCO2 fragments and OSCO3 fragments. That's one way of doing it. And then you can do the Wade-Mingos analysis. But anyway, give it a go at home and see if you end up with this structure.
But I don't get, like, I get where so many electrons that
Yeah.
I can't fit it
Yeah,
in all
but
of
you
it.
have to
But remember, the nuclearity is high. The
Yeah,
nuclearity
so-
is 8.
Yeah, maybe.
Oh, it's
Nuclearity is 8.
Amazing.
All right.
Good for them.
All right, guys, that's the end of the lecture. Next week we will be doing high-level NMR spectroscopy.
How do you get
good.
full